Welcome to part 3 of the Australian Biocommons Pawsey Supercomputing Centre's webinar series using containers in bioinformatics. In this session, we'll launch into scaling research using containers. I'm Christina Hall from the Australian Biocommons, and co-hosting we have Anne Backhouse from Pawsey, who'll moderate questions today. We look forward to hearing your questions throughout the session today, and our speaker will address your questions as we go. The way to ask questions is via the online discussion board at tinyurl.com/scale-containers. Please open this now so you're ready to go. This is a collaborative document. It's open for comments and questions, and feel free to address other people's questions if you know the answer. We have a couple of containers experts in there to help. Audrey Stott and Alexis Espinosa from Pawsey have generously offered to assist on the discussion board today. Now, questions put to the speaker throughout the webinar will come from this document, so please don't use Zoom's Q&A function. The discussion board will stay live after the event finishes for your future reference. You can also refer back to the recording of this session, and we'll let you know when the YouTube channels of Australian Biocommons and Pawsey will host those recordings. Once again, we have Pawsey Supercomputing Centre's Marco de la Pierre to take us through the webinar. He's a supercomputing specialist who works with researchers on challenges that include the design and deployment of containers for high-performance computing. Today, Marco will share with us his experience in scaling research using using containers. Over to you, Marco.
So welcome everyone to this third webinar in this series on containers for HPC and cloud with a focus on bioinformatics. So just quickly recapping about the previous 2 days. On Monday, we made our way through the introductory concepts of containers with Singularity. We saw how to share files between host machine and container to be able to run some practical research with containers. And then started on day 1 and then continued yesterday. We went a bit on detail on how to build containers with Singularity and most importantly Docker. And then we ran through some example of graphical applications that can be spawned using containers. Our focus today shifts a bit towards HPC topics. So we're going to cover MPI-enabled containers and how containers interface with resource managers and schedulers such as LERM and PBS. Then we're going to see how to effectively make containers writable, for instance, to tackle applications that feature intensive I/O, so creating, for instance, lots of files, millions of files and so on. And finally, we're going to quickly have a look at how to run GPU-enabled containers. So we're going to start today with a little demo using an MPI application called OpenFOAM, which comes from a different domain compared to bioinformatics. It's computational fluid dynamics, and actually Alexis from Pawsey here in the audience is actually our expert in the domain. If you want to match this type of example with bioinformatics research, you can think about some tools such as Hitmer or MrBase, which actually feature the possibility of running the analysis in parallel using MPI. So MPI is basically, for those who have never heard the word, stands for message passing interface. So it's a way to run an application in parallel. It means you don't spawn just one instance of the application, but multiple instances, and each one of the instances does a bit of the job that needs to be carried out for the analysis. And this way you get some speed up in terms of the total time that the analysis takes. This type of setup is very common in other computational intensive domains, such as computational chemistry, physics, and engineering. And it's making its way in bioinformatics for instance, with the tools that I showed you, that I mentioned you just now. So just making the screen a bit larger. So today, because it's HPC day, and I'm not gonna log in into my cloud instance, I'm gonna log in into Zeus, which is the high throughput cluster here at Pawsey, and I'm gonna run the demos in there. All right. me just move to the directory where the tutorial materials can be found. And just set a service variable that I might need later. Now let's move into the demos directory in the OpenFOAM one. And now let me show you the content of this script called npi pawsey.sh. It's a long script, but we don't need to understand it all. So we're just interested in some hotspots here and there. It's a script that is meant to be submitted onto a resource manager called Zerm. So for those of you that are Pawsey users, we might know it already because it's the main way to submit jobs and analysis on our HPC systems. So for instance, these first lines here, starting with batch, actually give you the idea that this script is meant to be submitted to Zerm. And for other people using other facilities, you might kind of set up similar scripts, for instance, using PBS, which is another resource manager, or other similar tools. Now let's go further down and see and focus on other lines in the script. So here we're just setting the name of the container image we're going to use for OpenFOAM today. Okay. And then here is the kind of the key part of the script. So it's been completely containerized. So it's basically 1, 2, 3, 4, 5 steps that are carried out by the script. Only one step is actually parallel, so actually uses MPI, the other 4 are serial. So let's have a look at how we are launching this application then. You can see, for instance, in the first step here, we are using singularity exec image name and a command similar to what we saw in the previous 2 webinars for any application to be launched with singularity. There is just one addition here, which is srun-n1, which basically instructs the resource managers Zerm to allocate 1 core for singularity to run. And here you can already learn something about singularity in HPC. Basically, singularity as a kind of a native interface to resource manager. So you don't need to do anything special in order to run singularity with Zerm or PBS. You use exactly the same syntax you would use for a non-containerized application. So if you add OpenFOAM outside the container, you do just run srun-n1 and the command. We are using the container, so we're just prepending srun prior to singularity. And that's it. You don't need to do anything more. You just use the syntax you would use with any other application. So that's quite almost transparent to users, I'd say. And the first 3 steps are all serial, so they all use just 1 core. Now let's move to the only step which actually uses MPI, which is the 4th step. And again, you can see it's kind of transparent and straightforward. So we are still using srun-n as a prepend to singularity. And here we are specifying not 1 as a number of cores, but we're using a Zerm variable, which is actually defined here, which is equal to 2. And so again, we want to ask the resource manager, say 2 cores for this task. Well, we just do the same thing we would do with any other application. Call the resource manager command for allocating cores. In this case, it's srun, number of cores, and then the very same syntax you got to learn in the previous webinars. So let's submit the script. For people that are not familiar with Zerm, this is achieved by using sbatch. So let's let it go. Okay, so it will just take a couple of minutes. Meanwhile, I'm gonna go back to the slide deck and discuss a bit what it takes instead to properly interface Singularity with MPI. Because what you saw in the script was just a very transparent approach. We just use srun and Singularity. But actually, to have the parallel component of the application to work properly, there is some work under the hood. That for Pawsey users has mostly been done by the Pawsey staff, so users don't really need to care too much. But if you are in a different HPC center, if you need to set it up your own, you might need to note down what are the key aspects to cover to get a working setup. So we said that there is a native integration with MPI run and resource managers. But as regards MPI, there are some aspects to be taken into account. So, of course, if you want to run an MPI application, you need your host to have a working MPI installation in it, and this will be basically satisfied in any HPC center, I reckon. And this is actually required for best performance. Keep in mind that in most HPC centers these days, all the compute nodes are interconnected using some high performance hardware. So basically some high performance fibers that allow the different compute nodes to talk to each other. And you need an appropriate installation of MPI on the machine for that to work at its best performance. So you need that. Hopefully it's covered by the system administrators of your HPC center. You also need an MPI installation in the container, and you mainly need that to build the software. Because if you need to compile an application that is able to run with MPI, you will need to embed that in at the compile stage. And normally this type of additional steps in the installation are covered in the documentation of the application. But that implies you do need some MPI installation in the container. You also need this third requirement that is normally the default behavior in Linux systems, so you should not worry too much. So when you build your application in the container, you need a so-called dynamic link between the application and the MPI libraries. And this dynamic character is the one that allows then the application at runtime to use the host machine MPI for running and achieving best performance. So this is why you need the dynamic linking, but this is the default in most Linux systems, apart from Craze. Good fun on Craze. So there is a couple of more requirements to be satisfied. So unfortunately, over the years, different MPI flavors or implementations have been designed by developers. And there are actually nowadays two families that are not compatible with each other. So because you need MPI in the host machine and MPI in the container, well, you need these two MPI installations to be compatible with each other. And this basically boils down to these 2 bullet points here. So mpitch, Intel MPI, MV-epitch, and Cray mpitch are compatible with each other. So you can have any combinations of those between host and container, and they will do the job. Whereas OpenMPI is there alone, so it's not compatible with the other flavors. So if you need to use OpenMPI in the host, you must have OpenMPI in the container as well. So that's a third requirement in terms of the MPI setup. And then final one, as I was mentioning before, what happens when you run the container, and this happens under the hood. The application will need to actually use the MPI from the host, not the MPI from the container, and that is to achieve best performance, because it's only the MPI on the host which has all of the proper configurations which are site specific, and these are the ones that allow to make the best out of the hardware of that specific site. And to achieve that, you need to define some singularity variables. Basically, you need to bind mount appropriate directories from the host so that the MPI installation in the host is visible in the container, a bit like we had to bind mount directories in the previous webinars to make input files available, pretty much like that. And then you also need to provide some similar directories with a second variable called the library path. And again, this is for appropriate configuration of MPI. So this can all sound a bit scary, and I'm gonna just give you an outline of how we have tackled this at Pawsey and basically made the life of Pawsey users almost transparent to these requirements, because it's basically all taken care of by the Pawsey setup. So what we're doing right now is that the mpitch implementation out of the 5 that I mentioned you is available in all Pawsey systems right now. That means that all we need to do if we want an MPI-enabled container is to install mpitch in the container as well. And to that end, we're making available in our Docker Hub a base image that is already that already ships with mpitch. So if people need to build an MPI application, they can start from that one, and the requirement of this compatibility will be already satisfied. And then, as regards the requirement of setting some appropriate variables at runtime for MPI to be configured in the container. Well, we've done the work already on 3 of our systems to set up the Singularity module with all the right variables. So basically the user will just load the module Singularity and they will get the proper setup for MPI already available. So basically that's why when the demo that I was running a few minutes ago on my terminal, I didn't have to do anything special. I just showed you the srun lines and that was all. But let me show you one more line then in that script, which I kind of skipped before. And this line is the line that says module load Singularity. So behind this, this line, there is a bit of admin magic that basically makes this last requirement to work. And I'm just very quickly and briefly showing for those of you that are more interested in this topic, how this module for Singularity looks like on Zeus at Pawsey. And again, this is not to confuse you. This is just to give you an idea of a visual idea of what you need you will need to set up in other systems to achieve this MPI performance. And basically, you can forget about most of this output, which is the content of the module of Singularity on Zeus. The key 2 lines are these 2. And you see that basically, this is the ones that are defining Singularity variables for MPI to work properly. You can see that we're quite lengthy. So here there was quite a lot of work for me and a couple of colleagues to get the right setup for MPI and Singularity on Zeus and other systems. So hopefully if you are on other HPC sites, you might ask kind help of administrators there and they will possibly sort it out for you. As we talked, the MPI job, the demo job that I submitted was finished. And you can see from the slurm output file that everything kind of went well. And we were able to run this analysis in parallel. And you should see a hint, here we go, that we're using 2 processors for this analysis. And this running a container at scale, sorry, at best performance in the HPC cluster Zeus. One very last slide before a small break. This is just to give you an idea of how the MPI performance with or without containers looks like, because people might wonder, okay, we're still running the application in a container. Is there a performance overhead? And I have a few figures and plots and data that were worked out by a colleague of mine, just to show you this comparison between native, so non-container performance and container performance. And the meaning of this graph is the following. So there are 4 nodes, so 4 compute nodes on Magnus that are exchanging bits of information between them using MPI. And on the x-axis, there is an increasing size of the information. So we are exchanging packets between 1 kilobyte and 1 megabyte. And on the y-axis with the latency, which is a measure of basically how long it takes to get the message transmitted. So the lower, the better. And of course, the larger the packet, the higher the times. But the key information here is that you can compare the blue lines and the red lines, and you see that they match. For each packet size, they're basically the same, which means you're getting the same MPI performance, whether you're using containers or not, which is really good. So there is basically no overhead in using containers with MPI applications. That's it. So I'm happy to take a couple of questions right now.
Yeah, there's some interesting dialogue. Some of it is very specific to individuals, but there's one that's kind of interesting, I think, at a higher level. If an MPI installation is only required inside the container for building the application, can parts of that, maybe the source or the development headers, be removed from the container after the build stage of the application? For example, via Docker staged builds or run, make, etc. Alexis is in the process of answering.
Yes.
He's thinking you cannot remove MPI libraries and keep a functional application.
To be honest, I never tried that. And so the reason why we're keeping the MPI installation in, I would say it can be handy for testing, for later testing, because I would say in principle, you might get the working application just with the host MPI. But in practice, you might be often in the situation where you just need to test whether the application is working, and then it's handy just to keep the MPI libraries in. So that's why we never tested that. So it's a good question. It might be worth trying. You can, for sure, you can get rid of the source codes. So according to the kind of good practices I outlined yesterday, so you can remove all of the source and just keep the final compiled libraries for MPI. And that will already save quite a lot of space in the container. Whether you can get rid of that as well and just rely on the host MPI, as I said, I didn't test it. In principle, it should work. I would still keep them just for testing.
And what about nodes? If there's a single node versus multiple nodes, does that bear any consideration?
No, yeah. So that's the thing basically. So there is everything is smooth and nice and actually performing quite well. So you can run OpenFOAM, for instance, at scale. So on even tens of or maybe hundreds of nodes with Singularity. Alexis did that with some researchers here at Pawsey. And you can get an idea from this graph here that there is basically no performance degradation. So it's a good practice. So if you need to containerize an MPI application, yeah, you can do it and get good outcomes.
Okay, thanks.
Thank you. So let's move to a second topic for today. So this one is possibly even a bit more interesting to a bioinformatics audience. And it's one of writable containers. So we saw in the previous webinars that a container file system is read-only. So normally if you need to write output files, you would bind mount a directory from the host and just write the files there. So normally you can basically work around this read-only character just this way by bind mounting. There might be cases where you might want to write files in a file system that is kind of embedded in the container and is not exposed directly to the host file system. When would you want to do that? Well, we found quite a good user case at Pawsey, and basically that's the reason why there is this topic today in the webinar. So there's a number of applications out there that have this habit. They were designed to generate millions of output files at runtime. And this might be not a big deal in local workstations and some file systems, but when you move to an HPC center, normally you have a parallel shared file system such as Lustre at Pawsey. And these file systems don't really like having to handle a large number of files. They rather prefer to handle a limited number of very big files. So when you run these applications generating millions of files on these file systems, you get quite a big performance degradation, which is actually not only restricted to the user of that application, but to the whole pool of users of the center. So it's quite kind of a problem actually to have a lot of these applications running on HPC centers. So to be honest, the proper way of tackling this growing number of applications that work with so many files would be at, say, at the level of the design of the centers, where you would allow for some dedicated nodes, compute nodes, who have a dedicated file system that is just tuned for this type of applications. But then needs to happen at the time you kind of set up your system, right? It might be kind of more difficult later on to provide this type of hardware setup in the center. And so what we kind of did was to look for software solutions, temporary workaround that are software-based to tackle this type of problem. And actually it turned out that Singularity can provide a good solution for this type of issue. And this can kind of hold on until we buy the next machine, and then maybe, hopefully, we will be able to actually provide some hardware solution to this type of problem. And why is this relevant to bioinformatics? Well, I can name at least a couple of applications that behave in this way. I used Albacore in the past, which is a base calling application for nanopore reads. this was kind of 2 years ago. The newer versions are behave much better, but the first iteration of that package was reading and writing millions of files. And then there is Trinity, a genome assembler that also tends to write a large number of files when you're working with large read datasets. So I think it can be quite relevant to have a look at how you can tackle this issue with singularity. So the feature we're going to use is called overlay FS, so overlay file system. And you need to know that in any Linux operating system, you can actually set up a single file to behave as an entire file system. So basically, you can create a big empty file in big gigabytes big or even more, and then use some Linux tools to make it look like a file system. So inside that single huge file, you can eventually write a huge number of files, and they will be hidden to the host file system. They would just look like a very big single file. So from what I just told you, it kind of sounds like a good solution, right? We can make the HPC file system just to see one big file, which it can handle very well. And then we can read and write a lot of tiny files inside this hidden file system. And you don't need to know much more than that, to be honest. So that hopefully this won't scare you too much. Basically, the way you achieve that is with a couple of Linux tools that you find in almost any Linux operating system. They're called DD and MKFS. And it's not the topic and the purpose of this example to teach you how to do this on your own. And that's because there is basically, here is on this slide, a pre-canned recipe for that. Basically, there's a syntax that once you get to know it, that's it. And I kind of written this down for you in a way where you don't have even to touch the lengthy part of it. You basically just specify the number of megabytes you need here in these variables, and then you do the rest. And so I have a copy of this syntax in my Zeus cluster here, ready for usage. And it's basically, let me clear the screen. It's basically in this file called create overlay, and it's exactly the same one. So I can run this script. Okay, so I am on Zeus, so I can't use Singularity unless I load the module called Singularity. So basically, it's kind of a recipe that you can take with you and use it every time if you ever need to create this type of bulky hidden file systems. After it has run, see there is a new file called myoverlay, which is 200 megabytes big, and that's the one that I created with this idiomatic syntax from Ubuntu. And once it's there, I can use it with Singularity. And so the last bit of information we need to discuss is how to achieve that. And it's quite straightforward. Basically, Singularity exec or shell have a flag you can use for that, which is -- overlay. And then you specify the name of this big hidden file system you just created. And then after that is the normal syntax. So image name and commands and so on. And let's see what happens. So first, let's run a Ubuntu container without that syntax. And for instance, let's open up a shell in a Ubuntu container, which is something we did on day one, right? It's syntax from day one of this webinar series. So now we are in. Let's try and create a directory. And I can't, because as we saw, the container file system is read-only. So now let's exit this shell. And let's now use overlay flag. So it's just -- overlay and the name of the overlay file that we just created. So now let's try again and create a directory. It now worked, and I can even write things in there. right. Just create some files, and you will see them there in this new directory I just created. And now we can exit the container. So are the files in the host file system? No, they're not. And that's because they got written in this overlay that we used with the container. And so this gives you the idea that you can create these new files using this overlay feature, but to the outside world, to the host machine, all of those files will always be inside this overlay file. And they will always be seen as a single file by the outside world. Can we reuse these files? So let us just try and reopen again another container, again using overlay, and see if the files are still there. And yes, they are. So that's really a way to have a kind of persistent storage that you can plug in the container and carry around with you, and it's just this single big file. So now let's create a directory here called output Trinity. And we're going to use that for a live demo of after this kind of almost meaningless examples of just creating little text files. Let us use this for a research demo using the Trinity assembler that I was just mentioning before. So as I was saying, yeah, Trinity is one of these bad guys that tend to write a lot of files. Here in this directory, I only have a small example. So I have this Trinity test data, just a couple of reads. I think they're quite small in size, maybe, yeah, just around a megabyte. So the run itself will literally take just a couple of minutes, but hopefully will give you the idea of how powerful this feature can be in your pipelines, data analysis pipelines. Because I have kind of goldfish memory, I've saved the full Trinity command for this demo in this file, just to avoid typing errors and so on. So let's try and use Singularity to run this Trinity analysis. And we're going to use the overlay feature. So we are going to plug in this big my overlay single file system. And then we're going to use this Trinity image today, which I have pre-cached before the start of the webinar, just to save some time, some download time. And then after that, let us just add the Trinity syntax, which basically just gives the location of the input files and some other options, including, quite important, the output directory. This is the last flag, output, where we want to put our output files. And as output directory, we're going to give the name of that directory I created in a couple of commands ago inside the overlay. And you might get a little warning at the beginning, but then that's it. So the Trinity pipeline is starting to process. As it goes, it will just take a couple of minutes. Let me just go back to the slide, just in case I missed on some important comment to share with you. No, I think that's all. So let us just wait a couple of minutes. And then I'm going to show you how the output from the full assembly pipeline looks like. And maybe actually to make possible to make good use of this time, maybe we can start and take some questions, because this part is basically almost over.
Okay,
I just have one last comment.
So there's some discussion around the use of MPI run.
Yeah.
And there's discussion around the Slurm scheduler, srun, etc. And then if you're using PBS, AP run. Mm-hmm. When would you be using MPI run?
So basically the only time, so MPI run is the command that allows you to spawn parallel processes when you do not have a resource manager. So you almost never end up using that one. You basically only use that in a computer that does not have PBS, so it has no scheduler at all. So I just put the mention of that just to give you the idea that Singularity is able to interface in a transparent way with all of these utilities. So including NPI run, which is the non-scheduler way of running parallel jobs, and also including any resource manager or most resource manager configuration. So it would be srun with Slurm, AP run, and now I can't recall the PBS syntax, but basically you almost never end up using write NPI run unless some scheduler uses that specific name. But I just know a couple of them, so I might be missing some.
Might it be?
But basically, the end up message is, if you're running in a center that tells you use srun, then you would use srun with Singularity. If you're running a center that says use AP run, you would use AP run. So there is no change in the way you ask for parallel resources and schedule and spawn parallel processes when you use Singularity or when you don't use Singularity. So it will be the same policies and that you would use for a non-containerized application.
Okay. And that would relate to, because it was a continued discussion from yesterday, and they are figuring out a way to use it in a batch job without using a launcher script. And so they included a template, and however they wanted to use NPI run, hopefully today's session would provide answers around that. And Alexis commented about, for Slurm, srun, for PBS, AP run, and then there was some discussion around MPI exec. So, yeah.
Yes, I would say no. If the scheduler is supported, the same syntax you would use in that machine for non-containerized NPI applications. You use it with Singularity as well. I imagine that it might be that not all schedulers are currently supported by Singularity. I don't have a list with me. I know for sure that Slurm and PBS will work with that. I'm not sure about other ones. And yeah, just one remark I'm just reiterating here is that you do not need additional syntax provided that the administrators of the machine have taken care already of the additional NPI variables to be set for Singularity. And so basically, I'm just thinking, I believe in the tutorial I put an example of how these variables look like at Pawsey. So if you are in doubt, you might have a chat with the administrators of the machine you're using and tell, hey, I want to use Singularity with MPI. This is what I think I need to set up MPI and interconnect libraries, which are the high performance connecting cables between compute nodes. I need this set up working at best performance. This is how we did it at Pawsey. Can you help me in achieving something similar here?
Okay, and then there's another talking about the overlay. So the current topic, 2 parts. What happens when a user writes more files and the overlay then reserved for it? And then is it possible to use the overlay file with Docker?
Okay, so of course, so here, let me show you the example we were working on, right? So I just cleared the screen. You can see that the analysis of Trinity is finished with no errors. Everyone's happy. You see the last output file has been written. Just clearing the screen. So in this example, I created an overlay file that was 200 megabytes just because I knew I didn't need more. Of course, if you fill that up, you will get an error from the application saying there is no space left on the device. It's a bit like filling up any hard drive, actually. So basically, you will need to estimate in advance how much you need and kind of create an overlay file that has enough space to hold your output files. And can it be used with Docker? I don't think so. So the way, and again, Alexis has also got some extensive experience here because OpenFOAM, So the CFD tool we use in the NP example also used to create a lot of files in previous versions. So Alexis has done quite a lot of work with researchers in figuring out how to best embed the usage of overlay on OpenFOAM as well. And basically, what sometimes you need to end up doing is to, once you've obtained your results in this overlay, which is this big, huge file, you might want to create a compressed archive inside the overlay. And once you have the single compressed archive with your output files, you can then copy it out the overlay, and then you can ship it around wherever it needs to be. So you might, just to say, you might need some extra steps in the workflow that handles this large million of files, because yeah, I'm not sure about the compatibility of these overlays with other applications. They use, so overlay FS is a general standard. It's a Linux tool. It's not Singularity specific. So might be that other tools that go, oh look, we are compatible with overlay FS. So those tools might be able to read and write possibly these files, but I've never tested that. And that's because, yeah, normally one way we've been going is to advise users to make a compressed archive of the output files and take them out that way, and then bring them to a machine which does not have the parallel file system issues. To say you might copy it. Honestly, any laptop can handle that large number of files better than a parallel file system, which can sound a bit weird, but that's the reality of things. Laptop file systems and HPC file systems are tuned and optimized for different types of workloads. But the important thing is you're not losing those files at all. So let me enter once more. Let me access one more the content of that overlay. And you see that even if I created the files with OpenFOAM container, I can access them with other container images. There is no restriction, and that's because the output files are created live inside this single file system, which is completely separated from the actual containerized application, which is then quite a good thing. It makes it very easy to access those files anywhere you have Singularity installed, basically. So now we are going to enter this container with an interactive shell, with a Ubuntu container, and I can now move into output Trinity. And here I have all of the output files that were created by the Trinity pipeline. In these examples, I think it's just a couple of hundred files, not much, but this can scale up. And I tested it with real research pipelines, and it was kind of working, and it was quite amazing. Just to give you an idea on the performance, actually, so was the example I have in mind was with this Albacore-based caller, and which was reading 1.5 million file and writing 1.5 million file. And just by running the same pipeline in an overlay file system, I reduced the runtime by half. So say from 2 days to 1 day. So it was quite a big performance gain. So not only I was reducing the workload on the file system for me and for the other users, but I also got quite a huge speed up. And that's because the parallel file systems really behave badly when you have a lot of files. I think we have time for another couple of questions after that.
I think we're good. Yep, there's some installation and reinstallation going on around Mac and Windows and Singularity. I don't know if you have any hints or tips.
I mean, I think to reiterate what I said yesterday, the best way, let me add one point actually. So Singularity guys, so if you go on the Scilab's website, they would suggest you to use a beta version of a tool called Singularity for Desktop, something like that, which I think works with Mac only. I tried that, then I uninstalled that because it's still in a beta. It lacks some key features. It also works in a different way compared to Singularity on Linux. So the syntax is the same, but the behavior you get is different. And I did not like that. So I'm just reiterating the suggestion I was giving yesterday, and which is documented actually in the online materials for these webinars. the best thing to do on Linux, on Mac and Windows is to install a virtual machine engine. Can be VirtualBox. My favorite these days is Vagrant, just because you can script it from the shell. Get one of these virtual machine tools. You install a Linux virtual machine, and then inside there, you follow exactly the same guidelines that you would follow in a Linux box. That way, you get exactly the same user experience that you would get on a Linux box, with the same features, with the same feedback from Singularity, and you're good to go. That holds, I would say, both if you want to practice any online tutorial on these topics. Once you have a virtual machine with Linux inside, you can you have access to a quite huge amount of training resources out there in a much simpler way compared to native Mac or Windows. And but also for testing and development purposes in your research. Once you have a working Linux virtual machine on your computer, you can do a lot of things. So I think Christina yesterday sent an email to the attendees of webinar 2 with a link to the specific episode of the online materials that detail the installation process. I think she will send the link again today. Let me just show you. So this is the online material. It's a superset of this webinar, so there are many more topics compared to what we covered in these 3 days. And one of these is setting up Singularity on your machine. And so you can take your time after this webinar and go through it. And there are the Linux instructions that are quite detailed. There is basically a template script that I've provided. But then there is the Mac and Windows trick in using Vagrant. And once you have a Linux box, you can basically do everything that is detailed for Linux in a Windows or Mac box as if you had an actual Linux box, which I think is quite powerful. Just bear in mind, all of these tools, so Singularity, Docker, any virtual machine manager, when you install them, you will need sudo privileges, administrative privileges on your machine. So that can sometimes be a problem with university institutional laptops, because often these days sysadmins just restrict your usage to non-admin rights. My take there is that if you convince them to install, say, a virtual machine engine on your laptop, and I believe after that you won't need to ask them sudo tasks anymore, because once you have your own Linux box, in there you can do whatever you want in a almost secure, safe way, and hopefully the admins will be happy with that.
One more question, time?
Yeah, I think we have time for the last one in this session.
Just quickly, do you want to say anything more about using overlay with Docker?
No, actually, so let me point out. The current best practices and recommendations at Pawsey are to use Singularity for running any containers, and that's we discussed a bit some of the reasons on the first webinar. I'm just reiterating that you can use Singularity on any operating system, any type of system from cloud, HPC, and workstation in a kind of consistent way. So I believe it's also a good way to try and identify one tool that is able to be used anywhere. So right now we're just recommending Docker for the build process. If you really want to use Docker there, there might be a way to achieve similar results with Docker volumes, but it's something I have not investigated personally. Might be possible. It will be a different story. I mean, I don't know on top of my head how you could use these in Docker. If you're really interested, try and send me an email. It might take me some days to reply on this specific topic, but I might have some ideas to share with you. All right, let's move to the last topic for today. So we're in HPC Day, so I believe it's important to mention GPU applications. They're becoming more and more popular across all domains of science. In the case of bioinformatics, I can tell there is a growing number, for instance, of assemblers that are moving to GPUs, and some base callers as well. I can mention Guppy again for Oxford Nanopore, and just mentioning that because we have a bunch of users, a growing community of users that are in that space. So actually, running GPU applications with Singularity is quite straightforward, possibly more straightforward than MPI or overlay. You basically just have two requirements. So the first one is on the host again. So if you're running your application and you want to run it on GPUs, well, your host computer needs to have a GPU. And so hopefully someone has installed the drivers for the GPU to work. So that's basically kind of automatic. Once you have the GPU driver, Singularity will be able to locate it and use it for running the GPU application. And how you achieve this, how do you tell Singularity to look for the GPU drivers and configure them for working? Well, all you have to do is when you execute the application, you just add this --NV flags, which stands for NVIDIA. So that's for NVIDIA GPUs. You add that, and basically Singularity will do the rest. So you will locate the drivers in the host machine and use the GPUs, the NVIDIA GPUs, to run the application. If you have AMD GPUs, there is a dedicated flag. I believe it's --ROCM. But so the message is, you just set this flag and basically the job is done. And I want to show this to you with one last demo. So this comes from kind of my previous life. So GROMACS is a molecular dynamics tool that has been imported to GPUs as well. And we have here, so let me submit this job first, this gpu.sh slurm script. All right, let me show you what this script contains. I don't care. I mean, the focus today is not about how to set up Slurm for GPUs. The focus is how I do set up Singularity for GPUs. And you can see the only major point that is worth a mention is that I'm using this --NV flag after Singularity exec. And that alone will make the GPU to be used by the application at runtime. Let me see if, too late. Let's have a look at the results here. That's the beauty of the live session. I believe there was an error in the input today. Apologize for that. No, wait, I know what happened. So there is a compressed input file here, which I forgot. Sorry for the hiccup. So let's give it another go. Let's rerun this application. And meanwhile, I will do something different. So I will have the possibility to connect to the actual compute node where the application is being run. And this way I can show you, I think, something quite nice. Every time I use GPUs, I always like to get a live idea that the GPU is actually being used. And so there is a tool that NVIDIA provides to monitor that, which is NVIDIA SMI. And you can see, let me go up a bit. So these nodes on Zeus have got 4 GPU each. And here, after this specification, there is a mention of the processes that are right now using the GPUs. And you can see there is the GROMACS executable GMX that is running on the first GPU here. And in fact, if you have a look at the summary for the GPU 0, there is a 46% utilization of the compute cores on the GPU. So we're actually using the GPU on Zeus using a containerized application that is GPU enabled, and we just had to add --NV on the runtime command line. And yeah, now the application is running. I believe it might still run for some time. So GrowMax is an iterative application. So we'll just keep on going through these steps that are here at the bottom of the screen for a while until it's finished. But yeah, that's it. So any questions on this last bit?
Yes.
Maybe we've got time for one. Possibly.
Yep. Just, I guess, in wrap up, you've already talked a bit about the tutorial materials.
Yeah.
Can you say a few things about what's on the GitHub repo?
Yeah, so basically the GitHub repo contains everything that allows you to run the tutorial, so including the markdown source files of the actual tutorial. So if you get this nice looking tutorials, it's that because there is some markdown files in the Git repo that are behind the scenes of these pages. And then the key thing, let me show you the repo. So there is a link at the bottom of each one of these tutorial pages. The key thing for you here is the demos directory, which is the one that contains all of the input files for you to run the examples in the tutorial. So if you git clone, and the first episode in the tutorial says that, if you git clone this repo, you can then basically follow all of the exercises line by line, provided that you have Singularity installed. There are some extra tools that are required for some more advanced examples, but I'd say if you have Singularity and download this repo, you have what you need for running the vast majority of the examples.
All right, thank you.
Thanks. And so just, yeah, it was my last slide. So again, these are the links for the tutorials, and today we covered the episodes 9 to 11. I believe it's now 18 in total. So I've been growing this over time. It's becoming way too big possibly, but yeah, it's there for you to use and you will stay there. So thanks all of you for attending today and attending the week of these webinars on containers for HPC and cloud. It's been a pleasure having you here.
We would love to hear from you, how to improve it, also how we can do more of these partnerships with Australian Biocommons. And there is the survey link right there. Again, we'd love to hear from you.
Thanks very much. Thanks, Marco. Thanks, Anne. Like everyone else, we are experimenting with online formats of events, and we've been lucky that we've had a large audience join us for this series from all corners of the earth. And we'd particularly like to know if you're interested in a follow-up with hands-on interactive online workshops. So please do take a few moments to fill in the survey there and let us know what you think. We'd also love to see you at some other events in the future. If you haven't already, please head to the Australian Biocommons website and sign up for our newsletter. It's a great way to hear about our bioinformatics news and events that are coming up. You must know by now that we have a YouTube channel as well that is a repository for all of our webinars and our workshop materials. And you can also hear about our events that are coming up at Oz Biocommons on Twitter. Now we have the some information here. And would you like to talk any more about how people find out about Pawsey events?
Sure, we'd love to. If you're not already a Pawsey friend, go to pawsey.org.au and you'll see on the top there, you can select Pawsey Friends and you will get information on events that we have coming up. So we would, we'd love to get that information to you. If you have questions, we also have a Pawsey Hour Ask Me Anything that's held every Monday from 10 to 11, Australian Western Standard Time. You'll meet individuals such as Marco and other specialists here at Pawsey, and you can, they'll bring your questions and they'll be there to help you. To sign up for that, you just go to pawsey.org.au/events. And thanks again for your time and attention. Thank you, Marco, for a great presentation, Audrey and Alexis for your chat and expertise in the discussion board, and you all for your time and great discussion, and Christina as well, and the Australian Biocommons for a great collaboration, which we hope to continue. So look forward to more events.
Well said, it's been a pleasure, thank you. And with that, I'd like to close by acknowledging that the Australian Biocommons and Pawsey Supercomputing Centre are enabled by NCRIS, and we'd also like to thank the Government of Western Australia and Bioplatforms Australia for their support. Thanks once again and goodbye.